Hello students, this video and those that follow over the next few weeks will hopefully provide each of you with a basic understanding of the math topics you will see next year. In each video, we'll review items already introduced to you both in this year and in previous years. We'll show you the next grade's additional standard and provide you sample problems to work through and to master before next year. It is recommended that for each video you have paper, pencil, a quiet work environment free of distraction, and at least 30 minutes to watch, pause, and practice. Remember, you can re-watch this video anytime during the week, and you can also receive extra information and help via Study Island or Google Classrooms with your teacher. So let's do a short little refresher course on what you've learned this year. Okay? We learned this year about rational numbers. Rational numbers includes the subsets of natural numbers, whole numbers, and integers. Rational numbers are numbers that can take the form of a fraction. For instance, 1/2 is a rational number, as is the number 4 itself. 4 can be placed over the number 1, giving you the fraction 4/1. Okay? Rational numbers include integers, whole numbers, and natural numbers. What we need to now learn is, of course, what irrational numbers are. Rational and irrational numbers are two entirely different things, but yet they have very similar looks. If we look here, these are rational numbers. 0, 5, 1/2, 0.5, 1/3. These are all rational because each of these can take the form of a fraction. 5 divided by 1, of course, is 5, so that's a fraction form. If I take the 0.5, well, that's the same as 1/2. So these are both fractions. 1/3, it's in the form of a fraction, but that 0.333 infinite, when that decimal repeats, well, that is a fraction. When you have a repeating decimal, that has a fraction with some sort of prime number in the denominator. In this case, 0.3 infinite is 1/3. 0.6 infinite, well, that's just 2/3. We can find that every single repeating decimal turns out to be just some sort of fraction. Now over here, we've got the square root of 25. Well, the square root of 25 is positive or negative 5. It can be either or. So the number radical 25, because this number is a perfect square, it can be reduced to the simple number 5, and that can be set as a fraction. So the radical 25 itself is also a real number. Now here's what we have here. We have terminate, repeat, or fraction form. Terminate means this decimal right here, 0.5, done. Everything else past that 5 is a 0. So this is called a terminating decimal. A repeating decimal is like that of 1/3, 0.333333. When a pattern repeats, we know it's a fraction. So all patterns that repeat are also rational numbers. Okay? This here, you'll see this very often. It says P over Q where Q is not 0. The definition of a rational number is a rational number divided by another rational number as long as that Q is not the number 0. So I can say 0/5, that's rational because 0 divided by 5 is 0. So that is a rational number. That makes sense. But when I take that 5 and divide it by a 0, well, now we get that big old E on the calculator error. If I have 5 pencils in my hand and I'm told I can only set them down in groups of 0, well, that's not possible. So that's where we get the error message. We cannot divide by the number 0. And that's what this equation is stating. The real rational numbers are rational if they take a terminating, repeating, or fraction form where the fraction does not have a 0 in the denominator. Irrational numbers, as opposed to rational numbers, never repeat and never terminate. Okay? Never repeat, never terminate. So if you look at the number pi is 3.1459, blah, 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 blah. It goes on forever. Okay, the last count I saw is they've got a supercomputer that's gone out to over 1 million digits. 1 million digits, and they still have not found an end to the pi number. So that doesn't make sense. I say the rational and irrational. What makes sense to a kindergartner? Okay, if I show a kindergartner, hey, I've got one pizza, well, that makes sense to a kindergartner, so that'd be a rational number. But if I told them I've got a building that is infinitely high, that's not really something they can grasp at kindergarten, so we call that an irrational number. Irrational numbers are infinite. They go on in that direction forever without ever repeating. So 1/3 repeated. Okay, we can actually write that as 0.3 with an infinite symbol over it. Okay, not the infinite symbol, but the repeat symbol. Okay, so that one is a fraction that repeats, so it is capable of becoming a fraction. But this guy right here, it does not repeat. 2, 3, 4, 3, 5, 6. There's no repeating patterning here, so it cannot do that. It does not have a perfect fraction for that particular number, so it is irrational. It's really hard to tell a kindergartner they could start writing an irrational number, and they would be writing that number long after they were dead, and the next person, their kids and their kids' kids would all be dead before that number ever got completed, because it will never end. Okay. Now hopefully you've noticed, I kind of skipped over it here, the square root and cube root symbols. Now these can be rational and they can be irrational. I just showed you that the square root of 25 is rational. Well, that's because the square root of 25 is, of course, positive or negative 5. So that can be converted to a whole number, and whole numbers are rational. I can show a kid that they've got 5 donuts, or I can tell them they owe me $5. Those are rational to a kid. But these ones here, if you put those into the calculator, they're going to give you a number like this. They're going to give you a number that does not end. Okay. The way I tell the difference is by looking at the number inside the radical symbol. Okay. In this case, that radicand is 3. The 3 is not a perfect square. 1 times 1 is 1, 2 times 2 is 4. So 3 is not a perfect square. So I know that I'm not going to have this lovely perfect little number like I did with the radical 25. So this is going to be irrational. The same thing with the cubed root of 17. Okay, if I think of that, 2 times 2 times 2, well, that's 8. So I go to the next one. 3 times 3 is 9, times 3, 27. 17 is neither 2 cubed or 3 cubed, so it's got to be somewhere in between. And it's going to be a repeating decimal as well. So if I see that square root symbol or that cubed root symbol, I have to look at the number inside. I can't just say, well, that symbol means irrational, because it does not. If it's a radical and then a perfect square, well, I've got a rational number. If it's a cube and a perfect cube, for instance, let's do this. If I do the square root of 64, 8 and 8 is 64, so that is plus or minus 8. If I do the cubed root, oh, excuse that, that's the bell over here at Manzanita. If I have the cubed root of 64, well, if I do the prime factorization tree, that's 8 times 8. Well, that's 2 times 2 times 2, and that's 2 times 2 times 2. Well, there's 1, 2, 3. Okay, I've got 3 sets of 2, and each of those is 4, so this cubed root is a perfect 4. 4 times 4 is 16. 16 times 4 is 64. So in this case, the cubed root and the square root both are rational numbers. But these two here, because they don't have that perfect cube, in this case they're both prime numbers, they are not capable of being rational. So they are irrational numbers. Okay. So with that, we have to make sure you guys understand that irrational numbers never end. They never repeat, never end. Okay. Because of this, we have to work with these numbers, especially in trigonometry and a couple other fields. We have to work with these numbers, and it's really hard to work with a number that never ends. If I start writing it, I'll be writing forever, so why would I use it? So we actually have to get used to comparing them, and later on, you're going to end up actually estimating them to 10th place, 100th place, etc. Okay. We also have to have a strong understanding understanding of density of numbers. Okay, if you haven't heard that term before, density of numbers means that for every two numbers, there's an infinite number of numbers between them. Okay, in the next video, video number 3, you'll actually see both of these concepts in action. Okay, now we're going to continue on with rational and irrational numbers. Okay. In irrational numbers and rational numbers, we ended the last video with the density of numbers. I'm going to actually start this part of the video with density of numbers to make sure you understand the concept as it is. The concept of density of numbers states that for any two numbers, 1 and 1.2, these are fairly straightforward. If you think about it, it's $1 and $1.20. Okay, we can find quite a few numbers in there just off the top of our heads. We can think of numbers like, I don't know, 1.1. Okay, 1.1 is between those two. What else is between those two? Well, 1.15. There's all sorts of numbers. Okay, so if I were to say 1.1, we know that 1.1 is halfway between 1 and 1.2. Okay, then of course 1.2 to 1.3. How many numbers are between there? Well, I can say, well, what about 1.25? Can't I have, instead of $1.20, can't I say I have $1.25 or $1.26 or $1.27? Each of those numbers falls between 1.2 and 1.3. Now if we look over here, I've got 1.30, and I can add that 0 in there. My pen works properly. I've got 1.30 and 1.31. Well, that's $1.30 and $1.31. Well, are there numbers between those two numbers? Well, actually, there's an infinite number of numbers between those two numbers. I can say 1.301. I can say 1.302, 303, 304. I can go even farther. I can say 1.300010. Okay? There are an infinite number of numbers between those two numbers. I can always just keep adding a decimal place like I did here. Okay? I just add a decimal place and I can keep going on and on. Well, 1.3101, 1.3102, 1.31000007. I can keep adding decimal places to this, and I can always find a number that's greater than this guy and then smaller than this one, no matter how many decimal places I go out. Okay? I like to show my students that big old huge 15, 20 zeros out here, and then 15, 20 zeros out here, and I can still add more decimal places to them to get smaller and smaller and smaller. And that's the density of numbers. I can always find more and more numbers between any two numbers, no matter how small. And because we can find infinite number of numbers between these two numbers, I can also do something a little bit farther. I can say, well, between these two, well, there's also 1.301. Well, that's a terminating decimal. So I've got rational numbers. I've got a rational number. And I actually have infinite numbers, rational. It's hard to write with a mouse. I have an infinite number of rational numbers between 130 and 1.31. There's an infinite number of terminating or repeating. I can also say, though, well, what about 1.3? Whoops, I'm going to switch over to the pen. 1.30. 1 0 0 0 1 0 1 2 3 6 7, and just kind of randomly throw out a bunch of numbers. Well, isn't that also, because it's 1301, well, that's small or larger than this number, but smaller than this number. So this, even if it goes on forever, that is still between those two numbers. Well, this is an irrational number. So what we like to say is the density of number states that for any two numbers I give you, no matter how big or how small, no matter what two numbers I give you, you will always find an infinite number of these irrational numbers and an infinite number of these rational numbers between the two. Okay, so in here, I've got an infinite number of rational numbers, 1.311. Oh, no, let's do 01. That's a rational number that's between these two. So is 1.31007. Those are both rational numbers between these two numbers, but likewise, in between these two numbers, I have an infinite number of irrational numbers as well, numbers that will never terminate. They just continue to go on and on and on. Okay, that's the density of numbers. So now we're going to look at this and understand radical compares to perfect squares. We're going to do irrational numbers to compare, and we're going to just estimate it. Later on, you're going to have to estimate to decimal places, but right now we're just going to compare them with the numbers that are already out there. Okay, so if I look at this, there's a reason I've got these 4 set up here. If we look at 3, if we already know where 3 is, we can put that on the number line right there. That's 3 is right here. Okay, there's our lovely number 3. Well, what about radical 9? Where would radical 9 be on this here? Well, hopefully you guys remember from previous practice that this is the same thing as positive negative 3. 3 times 3 is 9. Negative 3 times negative 3 is also 9. So both of those numbers equal 9. So we can say the radical 9. We're going to ignore, not ignore, we know it's there, but we're going to only worry about the positive value of radical 9 right now. And we can say, well, the square of 3 is 9, so that means the square root of 9 is 3. We can put that on the number line so that we know that the 3 and the radical 9 are the same. Okay, we can do the same thing with the 2 and the 4. We know 2 is right here, and 2 squared is 4, so we know the radical 4, the positive version of radical 4 is also 2. And we can label the entire number line like this. Okay. So I don't think I have it set up yet. We're going to test it. Oh, look at that. I do have it set up. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So these are all my perfect squares, and I put them underneath the radical symbol because these are equivalencies. 36, the square root of 36 is equal to 6. Okay, if I looked on the other side of the number line, it'd also say radical 36 is negative 6. Okay, and by doing this, we've given ourselves a way of comparing. So I look up here, radical 11. Well, radical 11, that's somewhere between 9 and 16. Well, 9, that's a distance of 7 there. So if I want to, I can go 1, 2, 3, 4, 5, 6, 7. I can break this off into 7 chunks, and I can say I'm at 11. So that's about there. The radical 11 is about right there. Okay. The radical 17, well, let's see if I've got that one saved here for you. Nope, I don't, so let's go back here. Okay, the radical 17, I do the same thing. I find the 16. Oh, that's real close there. So I can estimate that this is approximately equal to 4.1. Okay, just slightly larger than 1. Okay, so that's how we do it. We just kind of find our numbers and put it in here. Now this guy's a little bit unique. So is this one right here. That number out in front of the radical sign. So how do I put this in there? I know that 22 is right here. Okay, but what about that 2? That 2 says multiply 2 times radical 22. Well, 2 times radical 22 is a little bit different. What we're going to have to do here is we actually have to convert this to just a standard radical. So here's how you do that. You take your number out front, okay, and you're going to double it. As weird as it sounds, you're going to multiply this by 2. We're going to square this number. Okay, 2 squared is 4, so this is 4. And then we're going to multiply it by what's inside, 22. So this is actually 4 times 22. I put that in the radical sign, and I get 88. So this number is really the same as radical 88. Okay, so this 2 radical 22 is really way over here between 9 and 10. Okay, the square root of 88 is between 9 and 10 because 9 squared is 81, 10 squared is 100. Okay, now we do that again, also with the 2 radical 3. We take that 2 radical 3. We're going to square this number. Okay, that gives us 4. 4 times 3 is 12. So this number is the same as radical 12. Okay, so radical 12 is way over here. Okay, 9, 10, 11, 12. It's close to the left side. So I'm going to do that. Okay, it's way over there. Radical 12 is right in there. So we can start estimating our radical symbols. And now we can compare it to other numbers like 3.5. Well, this is slightly lower than halfway between 9 and 16, so this is less than 3 1/2. Okay, whoops, I did 3 1/3. Okay, and then we can start estimating it and comparing it to fractions, whole numbers, and other real numbers that are out there. Okay, now I'm going to ask you to complete some few. First, I think I recommend doing is actually completing the squares of each of these number lines, just like I did in the last step. The square of 1, square of 2, etc. And I want you to fill in the number line. Again, pause this video wherever you need to. fill it out on your scratch paper if you're doing scratch paper, so that you can get the practice in that you're not really going to get by just listening to my voice. Okay, hopefully you got this down. You should have created a 1, 2, uh-oh, did I put these as separate? That's all right. So we go in, click my way through this, and we've got our radical symbols up there. Oh, and look at that, number 18 automatically jumped in for me. So the square root of 18 is slightly larger than 16, so it's just barely bigger than 4, maybe a 4.12 or something like that, 4.15. We'll actually get into more accurate estimations later on. The square root of 50, well, there's the 49, and there's the 50. Square root of 60, sorry if I'm going too fast, oh no. Okay, radical 60, and finally, hopefully, radical 3, you put way down there on the left, just slightly below, or about a third of the way between, or 2/3 of the way between 1 and 2. Okay, again, these videos are not intended for complete standalone items. This is just to give you a basic understanding and help out the teachers. Your additional assignment is in the 7th grade week 1 assignment on on Study Island. Remember, this is a 1 attempt. This is not a normal Study Island. Make sure you understand the concept before you start. You'll only be able to complete this assignment once. Oh, there's that bell at Manzanita again. Okay, you'll only be able to complete this assignment once, so make sure you're paying attention to the topic. Watch the video a couple times. Go back and get help from friends or your teachers via Google Classroom before starting the actual assignment. If you need to, on Study Island, what you do is you search out the original concept. Oh, it's way back there. You search out this standard. So you're looking for an 8th grade standard. I know you're 7th graders, but you're looking for the 8th grade standard. So at the beginning of next year, you've got that one leg up on anybody coming into the classroom that hasn't watched these videos. So look for this standard, rational approximations of irrational numbers, and have fun with it, and good luck on your assignment.